Alright, this is Leontief video 2. So the goal of this video is to start looking at how to solve the problems that arise from the Leontief Input-Output models. So let me begin though with a simple definition. Let me redefine what the model was. So recall the Leontief input output model. This is the equation. P equals MP plus D. Few associated definitions. If you haven't watched the video before this, you definitely want to, because this won't make any sense. P is the production vector. So M is the consumption matrix. You could arguably, this is the internal consumption matrix, but the term is just consumption matrix. And so remember how this worked is the jth column, this corresponded to the requirements for sector J. So you may want to look back to the first video to make sure that that makes sense. D, this is the external demand vector. And MP, when we multiply those, we get the internal demand vector. So the goal in all of this, typically, is that M and D are given and we're looking for P. Now, we're going to divide this into a few cases, as we'll see. But just to begin with, suppose that we wanted to treat this just as an algebraic equation. So suppose we wish to be algebraic about it. All right, so you've got your equation. So you say, well, I want to solve for P. So what we'll do is we'll get all the P's on one side. Now we have to keep in mind that we're working with matrices and vectors here, so we have to be a bit careful. So when I factor out the P, I have to factor it out on the right, and I have to put an I in for the identity minus M times P equals D. And then I say, like, well, can I solve for P, right? I can't really divide by I minus M. That's a matrix, it doesn't make sense. So then you say to yourself, well, if I minus M is invertible, then I can multiply by the inverse, and then everything's great. Now, for what it's worth, most matrices are invertible, because remember, a matrix is invertible if the determinant is non-zero. And if you randomly throw down a matrix, probably the determinant is non-zero. So if this is invertible, this is mostly then you simply do this. Don't forget the inverse there. And we have a solution. So that's sort of the easy case. The other case is, what if I minus M is not invertible? So what I'll do first is I'll look at the invertible case. I just want to work through an example, point out some things, because there's sort of two subcases, an obscure one and a non-obscure one, or an obvious one and one just like to be aware of. And then we'll look at the case where it's not invertible, and I may put that in another video depending on how long the invertible case takes. So what I'll do is I'll clear the screen and we'll look at this equation when I minus M is invertible, do a simple example, look at a more nuanced example, etc. So 2, the I minus M invertible case. So let's take a look back at the very first example that we had originally in the first video. So this is revisited. So we had, I'll just say suppose this was the m that we worked out in the first video. So 0.1, 0.2, 0.25, 0.150, 0.40, 0.12, 0.30, 0.20. Now, suppose in addition, we had an external demand. And so what this is a vector that contains the total number of units that must be externally produced. Right, so in other words, this is for product 1, this is for product 2, this is for product 3. So how much must we produce overall? Well, the answer according to the formula is P is I minus M inverse D. So remember how this works. I won't rewrite every single gory detail, but we fill in the identity matrix. Subtract M, I won't recopy M, it's the one above. Take the inverse, this is invertible it turns out, multiply by our D. And so this tells us how much of each we must set production at. So this turns out to be 281.30, approximately 464.86, 695.34. Right, so this is what we do. We set production at this. In other words, you go to sector 1, you say, hey, set your production at 281.3. You go to sector 2, you set production at 464.86, and you go to sector 3 and you set production at 695.34. And everything runs smoothly, you get your external demand, your internal demand is satisfied, and everybody's happy. Now, little note here is this is the overall production. So notice how much of this being chewed up internally, right? The external demand was 100, 200, 300, right? So the internal requirements are fairly large. So note, the internal demand is, we take this vector, this is everything that's being produced. You subtract the stuff that's going externally, and if you look at this result, right, this is 181.30, this is 264.86, this is 395.34. This is all being used internally. That's just sort of, I'm not saying it's good or bad, I'm just saying like that's an interesting fact, right? The 100, 200, 300 gets sent out. This is all chewed up internally as part of the process. Right? Now, just a second example, this will be really quick, is notice what happens if D is 0. Right, so if I minus M is invertible and D is 0, so if you look on the left-hand side, if this vector right here was 0, then this vector would be 0 as well. Right? So I'm going to say example, but I'll make this generic. Right? If I minus M is invertible and D is 0, then what happens? Right? P must also be 0. Oops, 0 bar. So P is 0. So if I minus M is invertible and the external demand is 0, then nothing gets produced. It basically doesn't work, right? So we cannot produce. So what's happening here, this may seem a bit weird, but what's happening is like there are inefficiencies such that if you ramp up any production at all, things are not all being used internally. And as a consequence, Like you almost have to have some external demand, otherwise there's like continual waste of things that is just necessary as part of the economic system here. So let me clear the screen now, and then we'll look at the case where I minus m is not invertible. And again, there'll be sort of a couple different subcases, but they're all pretty manageable. So 3, I minus m not invertible case. So what I'm going to look at first is I'm going to divide this up as follows. I'm going to look at the case where d is 0 first. There's a reason for this. So in this case here, our equation, so remember our equation got rewritten like this. This becomes I minus m p equals 0. Now, if we rewrite this again, I'm going to sort of backtrack a little bit. This can be rewritten as ip minus mp. We could have just gone back to the original equation, original Leontief Input-Output model, that's all right. And I can rewrite this, and ip is the same as 1p, just literally the number 1. So the reason we rewrite this is we're looking for a p, and this equation corresponds to having an eigenvector with an eigenvalue of 1. So basically what's happening here is that this will be satisfied if and only if lambda equals 1 is an eigenvalue of m, and then p will be an eigenvector. So note that otherwise 0 will definitely work. I mean, basically p equals 0 always works because p equals 0 always satisfies this equation right here. But what we're really interested in is, are there other ones? And so when we say this will be satisfied, what we mean is by p non-zero, like when we will get, when will we get an interesting result? Right. So take a look at a really, really simple example. Well, it's not simple, but a not too bad example. So if we consider this consumption matrix, now I sort of specially designed this to do the job. Right, so this consumption matrix, this is that's just a 0, 0.9, 0.1. This does have an eigenvalue of 1. Like in this particular case, I minus m is not invertible. In this particular case, m has lambda equals 1 as an eigenvalue. If you're a bit rusty on eigenvalues and eigenvectors and how to compute them, that's okay. We can be doing a bunch of this using MATLAB, and we'll sort of work out any rusty details as we go. So lambda equals 1 is an eigenvalue, and one eigenvector is this. I just sort of pulled this out of MATLAB. And MATLAB tends to give unit eigenvectors, so this is an eigenvector with length 1. But if you remember something about eigenvectors, is that any multiple of an eigenvector is an eigenvector. So in theory, you could set production as this. Or any multiple of this. Right? So there are lots of productions that will work, right? So we could, for example, have p being, say, I could multiply this by 10. could multiply it by 1,000. Or I guess 10,000 in this case, etc. So again, any multiple of an eigenvector is an eigenvector. In this particular example, we have a non-invertible I minus m. However, and again, this example is specifically designed to work nicely. And if you're a bit rusty on eigen stuff, it might be a bit confusing. That's okay. But it has lambda equals 1 as an eigenvalue. It has this particular eigenvector given by MATLAB that corresponds to that eigenvalue. And then any multiple of that will also be an eigenvalue. So any one of these things will work. So let me clear the screen. I'll look at one last simple example just to sort of round things out of when I minus m is not invertible and d is not 0, and like how that can possibly arise. So b, we'll say I minus m not invertible and d not being 0. So this can arise and can have solutions. We won't focus on this too much, but I just want to point out one because it leads to some sort of interesting economic facts. So look at an example. So for example, say this particular m So I want to point something out in this, just a reminder of what all these values mean that'll be helpful. Right? So this column right here, forget that little pink line right there. This column, this is telling us the requirements for product. This is the requirements for sector 3 to produce 1 unit of product 3. So if you notice, it doesn't require any product 1. It doesn't require, I should say produce, this is a bit confusing. It doesn't require any product 1, doesn't require any product 2, but it requires an entire of its own unit of product 3. So no product 1 required, no product 2 required. So in this particular case, sector 3 only needs 1 unit of product 3 to produce 1 unit of product 3, which seems a bit goofy, right? It's like it's using up all of its own product, right? So it's, for example, it's like, suppose you had a farmer, and the farmer, to produce a pound of wheat, was so hungry that he or she needed to use up 1 pound of wheat, right? So this is kind of a goofy situation, but it's realistic, right? The farmer could produce a pound of wheat and eat that wheat, make it into bread, whatever, and then consume the wheat and use that energy to produce another pound of wheat. And nothing ventured, nothing get, like, it's sort of goofy, but it's okay, right? Now, if we look at these other two values right here, what those are saying is that sectors 1 and 2 don't require any product 3. So sectors 1 and 2 require no product 3. So what this means is basically is sectors 1 and 2 can do whatever they need to do to have an external demand. And sector 3 is sort of isolated by itself. So what's happening here is that sectors 1 and 2 operate independently. We could think of them as an isolated little economy. Right? This matrix actually has I minus m being invertible. Right? This is for those. And then sector 3 just produces whatever it wants. Or it's off producing and consuming all of its own product. We just ignore it. So for example, we could have something like some D. You could make up a D like this. This could be anything you like down here. So sectors 1 and 2 do these. Right, up here this I minus m is invertible. And then sector 3 does this by itself. This is sort of an esoteric example, but it's sort of a good one to end on, to just sort of make the point that like we can have these weird situations where basically one sector of the economy is isolated off from other sectors of the economy and it's just operating on its own. So let me stop there. So we have some broad ideas about how solutions of these arise, and in future videos we're going to look at sort of some more esoteric details as to what's going on mathematically under the hood.